Thank you very much. Thank you for the invitation. Thank you to the organizers for organizing such a wonderful conference. So the spirit of this talk is really captured in the subtitle. This is a way to think about delta-matroids if you're really mainly focused on matroids. And we're going to use Higgs lifts in order to do this. So this is joint work with Carolyn Chun and Steve Noble, and the slides are on my webpage. So. Fortunately, we already had a nice introduction to delta-matroids, so I can go a little bit quickly over parts of the background, but I'm going to emphasize certain pieces that we're really going to need. We're going to work inside the context of set systems or hypergraphs. And a set system or hypergraph is a pair consisting of a set together with a collection of subsets. We always call those subsets feasible sets. And our model really is you take a matroid. The set is the ground set of the matroid. The feasible sets are the bases. Okay? And that's a good example because it's a proper set system, which means that there are feasible sets. So those are the only ones we're going to be interested in, proper set systems. As Goran explained, there's the definition of a matroid that we're all familiar with in terms of bases. And yes, you replace set differences by symmetric differences, and you get the definition of a delta-matroid. So your feasible sets have to satisfy that axiom. For any pair of feasible sets x and y and any element u that's in just one of those sets, there's a v, possibly equal to u, in, again, just one of those sets, so that x union the symmetric difference of the set uv is feasible. Now, I don't know about you, but when I saw the definition of a delta-matroid for the first time, it took me a little while to digest everything that actually is allowed by that. So let me first spend a little bit of time just unpacking that definition. So we could, pick an element u that's just in x, okay? And if u is equal to v, in that case, we'd just be taking u out of x. We could potentially pick v to be another element that's just in x, in which case we're removing two elements from x. Or if we have v just in y, we're doing what we think of as an honest exchange, the exchange we're used to. And similarly, u could just be in y, and maybe we're adding just just u to x. Or maybe we're adding u and another element to x, or maybe we're doing a real exchange. So there are a lot of possibilities, and you see right away that the sizes of the feasible sets don't have to be the same in a delta-matroid. Okay, another bit of background that's going to be very important in this talk is quotients, lifts, and in particular Higgs lifts. So let me remind you of these things. So if you take two matroids Q and L on a set E, we say that Q is a quotient of L if there is some big matroid for which L is the deletion, a deletion of that matroid, and Q is the corresponding contraction. So in other words, you can take L, add some points to it to get this big matroid M, and then contract those, or look at the matroid from the perspective of those points and get the quotient. So that's what a quotient is. Here's just a good example to keep in mind. We'll use it as a running example for a short time. Start with the uniform matroid U59, so rank 5, 9 elements. And let's consider 3 disjoint planes, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now you take a pair of those planes, and you could add a point to them, because this is all in, the pair generates rank 5, not rank 6. So you could actually add a new point to a pair of planes. And you can do that for each of the 3 pairs of planes there. And then you could contract those new points. So what's the effect? Well, you added 3 new points. You're down to rank 2. Each triple of points, each of those planes, gets 2 new points added to it, because it's in 2 of these pairs. So that plane gets contracted down to a point, so 3 parallel points. So you're getting these 3 parallel clusters of points on a line. That's the quotient. Okay? The Higgs lift. So given this quotient lift pair, you can define a new function. For each set x, you take the minimum of the, pick an integer I between 0 and the difference in the ranks. Okay? And then for each subset X of the ground set, you take the minimum of the rank in the quotient of X plus I and the rank in the lift of X. So basically, you're allowing the rank to go up by I compared to the quotient, provided that doesn't go above the rank in the lift. The lift provides an upper bound. And one can check that that is the rank function of a matroid, and that's the Higgs lift, the ith Higgs lift of Q towards L. So let's just look at that in the example to make that clear. So our quotient here was this line with three groups of parallel lines on it. You lift once, and each of those classes of parallel lines becomes a 3-point line. Sorry, each of those classes of parallel points becomes a 3-point line. And the whole thing goes from rank 2 to rank 3. So you're getting these three three-point lines in rank 3. You lift again, you lose the 3-point lines, you get a uniform matroid, and lift again, you're back to your original uniform matroid. So why is the Higgs lift important? It has a lot of nice properties. It's the freest quotient of L of the rank of Q plus I that has Q as a quotient. It has a very nice description of the bases that's going to be crucial in what we do. The bases of the Higgs lift are the sets of size rank of Q plus I that contain a basis of Q and are contained in a basis of L. Okay? That relation is going to be crucial to what we do. Any questions so far? Everybody's okay? All right. Now we can get a delta-matroid from Higgs lifts this way. You take a collection of those Higgs lifts, and we actually don't have to take all of them. We can just, we don't want to skip consecutive levels. Right? And what we're going to do is we're just going to take the union of the collection of bases of this collection of Higgs lifts. So let me just illustrate the symmetric exchange here. So X is a feasible set because it's a basis of Q. Y, this 5-element set, well, that's the basis of the uniform matroid. U is just in Y. And, well, let's see, I could do a couple things. I could go to 1, 2, 4 because that's a basis of the first Higgs lift. Okay? I can't add another element because I didn't put any rank 4 matroid there. Okay? But I can actually do an exchange, and I can exchange to get 2, 4, which is a basis of Q. Okay. And the general theorem, another example, a general theorem that's actually very easy to prove, but it's the context of what we're doing, is this. Whenever you have a quotient lift pair and you look at this collection of Higgs lifts, and you do what we just did, take sets that are bases of any one of these, okay, as the feasible sets, you always get a delta-matroid. And in fact, you can leave out any particular level of that, provided you don't leave out 2 consecutive ones. Okay? Now, this particular construction in the special case of taking all the layers has actually been known for a while. We call it the full Higgs lift delta-matroid of the pair, but Eva Tardos was studying it in the late 80s under the name of generalized matroids. And it appeared again recently in a paper on the archive by several people here under the name of saturated delta-matroids. So, and generalizing it to this it's not a big step, but it's important for what we do. The next thing I want to do is I want to give you a very concrete example of this construction to help fix it in your mind. And it's going to be generalizing lattice path matroids to delta-matroids. So let me just quickly review lattice path matroids. So for lattice path matroids, you have 2 bounding lattice paths, P and Q, both going from 0, 0 to your favorite point, MR in the plane, with P never rising above Q so that they bound a region. Okay? And then you consider all paths from 0, 0 to that favorite point that stay inside of that region. Think of them as words in the alphabet east and north. Okay? And then with each path, you can look at the set of positions where the north steps occur. Okay? So by looking at all paths, we get a collection of sets. Guess what? They are the bases of a matroid, bases of a transversal matroid. And these are lattice path matroids, which Jim Lawrence referred to the other day. He had actually been looking at them in connection with concatenation. He was looking at them in the early 80s. We independently rediscovered them, but gave it that interpretation. So this is joint work with Anna Demir and Mark Noy. And I just mentioned briefly, these are actually really quite interesting matroids. They have a lot of nice properties. It's a minor closed, dual closed class of transversal matroids. They're not quasi-ordered. There are infinitely many excluded minors, but you can actually write them all down. And one of the most surprising properties, you can compute Tutt polynomials in polynomial time. It's just ridiculously fast to compute their Tutt polynomials. And because they're sort of that sweet spot between a substantial class, but something that's concrete enough to really get your hands on, people have been doing a lot of things with them in recent years, proving special cases of conjectures for them and so on. So they've really grown. So now, to generalize them, we're going to again have two bounding paths, P and Q. They're both going to be of the same length, but now they don't have to start and end at the same point. Okay? P is going to start at SP and end at TP. Q is going to start at SQ and end at TQ. And the line through those starting points has to have slope -1. The line through the ending points has to have slope -1. I want TP to, let's see, what do I want? I want TQ to, so the last point of Q I want to be to the right of the line through S0. And similarly, I want TP, the end of P, to be above the line, the horizontal line through SQ. And then that gives me a nice region, okay? And now I can consider paths in that region, starting at one of the points on that line of slope -1, ending at a point on the other slope line -1. And again, what we're going to do is we're going to look at the positions of the north steps in these paths. Now notice, these paths are not recorded by their north steps, because if I take that and I just shift it up a little bit, I'm going to get the same sequence of north paths, but I'm going to get another path in the region. Okay? So it's not the bijection that we actually had before. Now, there are a couple of, let's see, did I? Yeah, so again, we're going to look at the set of these sets of north positions from north steps. There are a couple that stand out. So if I start at SQ and end at TP, those are going to have the fewest north steps in them. Okay? And if you look at those, there's a lot of the diagram that just plays no role, so you can forget about it, and you get the diagram of a little lattice path matroid. Okay? So the sets of minimal size that you get are the bases of a lattice path matroid. Similarly, if you start at SP and end at TQ, those are going to have the most north steps. Okay? So there's another lattice path matroid. And the theorem is that that min guy is a quotient of the maximum lattice path matroid there. And what you're getting in between are exactly the Higgs lifts. Okay? And this gives you a minor closed and dual closed class of delta-matroids. There are other things I could say there, but I need to move on. This actually illustrates what happens with delta-matroids in general. So this is a result, or a compilation really, of results from Bouchet. Whenever you have a delta-matroid, if you look at the feasible sets of maximal size, you will have a matroid. We call that Dmax. If you look at the feasible sets of minimal size, those are the bases of a matroid. We call that Dmin. It's always true that Dmin is a quotient of Dmax. And each feasible set contains a basis of Dmin and is contained in a basis of Dmax, which should sound very familiar. That sounds like the description of the Higgs lift, right? Except we don't have all the sets. And that's the whole point, that these Higgs lift delta-matroids provide, to some extent, a universal model for delta-matroids. Any delta-matroid sits inside of this. You've just removed some of the feasible sets. It's sort of like any graph sits inside a complete graph. Right? So that sort of thing. Except with graphs, you don't have to be careful what edges you delete. Here you have to be very careful. Okay? So the next part, and the main part of the talk, really is, what do you have to avoid when you delete some of the feasible sets? So what we have is an excluded minor characterization of delta-matroids within this really broad class of set systems. So we need to define minors at the level of set systems. First, you have to be a little careful for loops and co-loops. So loops are elements that are not in any feasible sets. Co-loops are elements that are in every feasible set. Okay? So now, consistent with what Goran said for deletions and contractions and delta-matroids, we take the same definition. If you have an element that's not a loop, so there are some feasible sets that contain it. In order to contract that, you just reduce your ground set by that element, look at the feasible sets that contain that element, and get rid of them. Get rid of that element. Similarly, for deletions, if you take an element that's not a co-loop, so there are feasible sets that don't contain it, you look at those sets, the feasible sets that don't contain it, you reduce your ground set, there's your deletion. And of course, minors are combinations of deletions and contractions. Now, there are some things you have to be careful about when you work at the level of set systems, namely, the order of operations can matter. So you have to have ways to get around that. Okay. There's another important operation, generalizing one that Goran mentioned. He mentioned the dual. There's the twist, or partial dual. If you take a set system and you take a subset, you just replace every feasible set by its symmetric difference with that subset, that fixed subset. So for instance, if you take U24 and you write down its bases, as in the first line there, and you twist by the set 1, 2, then you get the collection of sets on the second line, which you see don't all have the same size, so they're not the bases of a matroid. So partial duals of matroids don't have to be matroids. But minors and twists of delta-matroids are delta-matroids. And this partial dual allows you to relate deletion and contraction. Okay. And it's also an involution. Okay. So now we get to the excluded minors. So let's see, what are some obstructions to being able to carry out the exchange? Well, one obstruction would be having a feasible set, having a feasible superset that's sufficiently much larger and nothing in between, right? Because the exchange just allows us to delete one or two elements or add one or two elements. Okay? So a minimal case of that would be taking the empty set and a set with at least 3 elements and nothing in between. Okay? That's these sets SI, or these set systems SI. Another possibility would be having a feasible set, having a larger feasible set, and having all of the feasible sets other than the bottom one contain a fixed element, so that I can't get rid of that fixed element in the larger feasible sets. So here are 8 ways to achieve that, 8 minimal ways to achieve that. A is the element that's in all of the larger feasible sets, except the empty set. Now, you also have to allow the twists of all of these guys. So the S's, they have their twists. This list of 8 has its twists. There are 51 twists of those. And you put them all together, and you get the feasible sets. Sorry, you get the excluded minors for delta-matroids within set systems. And so that's an excluded minor characterization of delta-matroids. Now, of course, once you have this machinery, you can apply it to a lot of things. So, in particular, matroids are special delta-matroids, right? They're the delta-matroids where all the feasible sets have the same size. So now you can come up with an excluded minor characterization of matroids within set systems. And all you have to do is you have to just look at our list and see, let's look just at set systems where all the sets have the same size. Okay? Look within our list of excluded minors. Look for those where all of the sets have the same size, and there you get your list. So you can create a lot of things like this. And just to end kind of quickly with a few other things, just to flavor things, obviously not details. You could consider delta-matroids. So when you have a delta-matroid and you have all these levels, only the bottom and top have to be matroids, right? What's in between on a given level doesn't have to be a matroid, but it could be. So you could consider like stacks of sparse paving matroids or paving matroids. So you can actually give excluded minor characterizations of these stacks of sparse paving matroids. You can do the same for paving matroids. You can do the same for stacks of quotients. Right? As you go down, each matroid you get is a quotient to what was above. So we have excluded minor characterizations of those. And let me just end with, saying, so I've talked about this very nice example, right? These lattice path delta-matroids. Hopefully that inspires you to think about that example and develop more. I've talked about excluded minors, but I haven't connected the two. I do know that there are infinitely many excluded minors for these lattice path delta-matroids. Finding the complete list looks hard, but it also looks like an interesting problem. So I just mentioned that as an open problem.